We are going to continue talking about inferences for a population parameter. Now this parameter is the variance. So here's this diagram that we've seen all semester long. Let me get my red pen out here. Where we have this population. It's hard to get at every item in the population, but what we're very interested in is how variable, or how much variability, I should say, is amongst these items in terms of the numerical quantities. And we denote then this variability by the variance, the Greek letter sigma squared. Simultaneously, we could also be talking about then the standard deviation as well. So what we do is we go into the population, we take a representative sample out of that population, and now we have a smaller set of information that's much easier to work with. This is what's called our sample, and we can calculate a numerical summary measures for this sample, the sample variance. Then using this sample, and especially the sample variance, we can draw inferences back to the population so that we can better understand it. Now, I must admit that doing inferences about the variance is less of interest than it is for, let's say, like a population mean. But there are a number of situations, as you will see very shortly here, where this would be of interest. In particular, where inferences for a variance is of great interest is with respect to investing. Sigma squared in investing is often equated to a measurement of a risk for a particular investment. So for example, let's say that you're interested in maybe buying some shares of a particular stock. And the stock one day might be selling for $41 a share, the next day $42 a share, the next day maybe $41.75 a share, and so on. And also, suppose there's another stock out there representing a similar company, and its per share price on one day was 30, the next day it was 15, the next day after that it was 40, the next day after that was 25, and so on. And if we think in terms of a sample variance, I think you will agree with me that, let's say, stock 1 has a lot less variability than stock 2. And because of that, an investor who is, let's say, risk adverse might be more interested in purchasing stock 1 than stock 2, because there's going to be a lot less variability in the stock price. Another place where the variance, making inferences about it, is very important is with respect to quality control. For example, let's say a company that produces frozen pizza wants its pizzas to weigh, on average, 16 ounces, but will tolerate a standard deviation of 0.1 ounces. So, every single pizza that's made is not going to weigh exactly 16 ounces. Sometimes you might have a few extra shreds of cheese on a pizza, or a few less shreds of cheese. But generally speaking, a particular company wants to control the quality of how close they're always getting to, let's say, 16 ounces. And so what could be done is that on the, let's say, the assembly line of creating these pizzas, maybe 16 pizzas are sampled from that process. The variance and the standard deviation is calculated for the sample, and then using this information, the sample, inferences are drawn back to what the population variance standard deviation would be, so that a company can determine if their manufacturing process is in control, meaning that they're making everything as they would expect, or out of control. And in that case, you would probably want to stop the manufacturing process and see how they can fix things. Okay, so remember that sigma squared is estimated again by the sample variance. Here is the sample variance written in terms of, let's say, observed particular values. So that's why I have a little s squared there. And if we take a look at the equation again, we'll notice that what we do is with every observed value that we get, y sub I, we subtract off the mean and we square it. So what we're going to do is actually look at the square deviations from the mean. The bigger these square deviations are, the more variability. The smaller these square deviations are, the more the less variability. These y's are more around the mean. And so for all observations in the data set, we add these squared deviations up, and we divide by n minus 1 to get sort of like an average value of these squared deviations. Now, in a mathematical statistics course, you've heard me mention this kind of a course many times before, what one would do is actually prove why we are dividing by n minus 1 rather than n to get an average-like value. And obviously, in this particular class, we're more concerned about the applications and understanding interpretations of particular quantities, so you don't need to worry about proofs like that here. But I want to give you some intuitive feel for why we divide by n minus 1 rather than n. Well, let's say that we did divide by n, and working with now the random variable version of some kind of an average sample variance. So now I have the capital Y's in there. One could actually derive what the expected value would be. And notice it's not exactly equal to sigma squared. Instead, it's n minus 1 divided by n times sigma squared. And so what you could do then is, instead of dividing by n minus 1, suppose instead you divide by n. Instead of dividing by n itself, suppose we divide by n minus 1 instead. And when one does that, one can actually prove mathematically that what I would expect s squared to be on average is equal to sigma squared. What is trying to estimate? So that's why we work with this n minus 1 rather than n. Now, in order to do inferences about the variance, sigma squared, or again the standard deviation sigma, we need to introduce a new probability distribution called a chi-square probability distribution. So this chi here is the Greek letter chi, and sometimes you'll see people actually write it out like this, the chi-square distribution. So the square part comes in because when this probability distribution essentially was first developed, there were components of a particular statistic that had a square to it, and so that's why it's called the chi-square distribution rather than maybe just chi itself. So this is just another probability distribution, like a normal distribution, like a t-distribution. So because of that, there is going to be some equation associated with it that would allow us, for example, to plot it. And so let's say we have a continuous random variable x. It has a chi-squared distribution, and it has one parameter associated with the distribution, the degrees of freedom, which we will call nu, N-U, just like what we saw with the t-distribution before. And so then this probability distribution, we can write out a formal expression for it. You don't need to know what this formal expression is, but I just want to show it to you that so you can see that indeed there is something out there that's what's generating these plots that we're going to see. And the expression is f of x is equal to, and we look at two different cases, when x is greater than 0 and otherwise, when x is less than or equal to 0. And notice f of x is simply equal to 0. So essentially the borderline is at 0, and we're looking at positive values for x. And so for this distribution, we take 1 over 2 raised to the degrees of freedom divided by 2 power. Then we take it times the gamma function evaluated at nu divided by 2. You may remember with the t-distribution, the gamma function played a role in that. Then we take x raised to the nu divided by 2 minus 1 power, and then e raised to the negative x divided by 2 power. This is the chi-square distribution. Note that there's a special case of the chi-square distribution, and that is, let's say if nu is equal to 1, then if I have a random variable x that has a chi-square distribution, this is exactly equivalent to a standard normal random variable that is squared. And we've come across that before. Just like with any other probability distribution, the corresponding random variable has a particular mean and a particular variance that you can actually derive itself. So the expected value of x is simply the degrees of freedom, nu. The variance of x is 2 times nu. And we got to be a little bit careful with our notation here. Maybe I shouldn't have done this here. Notice how I have a sigma squared there. This is different from what we're making inferences to. Very frequently, sigma square is used to represent a variance for a random variable. Well, when we're working with a probability distribution, like the chi-square distribution or the normal distribution, the t-distribution, or there's many other distributions out there, very frequently when one talks about the variance of x, often one denotes that symbolically by sigma squared as well, and so that's where that comes up. So, maybe it might be just easier just to remove that. Okay. So, just like with other probability distributions, we're very interested in finding quantiles. We're very interested in finding probabilities associated with the corresponding distribution. And so, we need some way to symbolically denote, in this case, a quantile in a generic manner. And so we're going to use the notation chi, that's the Greek letter chi. We square it. That's just a symbol, okay? And then we have alpha divided by 2 in the subscript and also nu in the subscript. And what this denotes symbolically for us is the 1 minus alpha divided by 2 quantile from a chi-squared distribution with nu degrees of freedom. So this is what it looks like then. So let's just ignore this part on this side for now. Similar to what we've seen with the t-distribution and the normal distribution, that in the subscript there, where we have this alpha divided by 2, that means the area to the right of this particular number. So that means the area to the left is 1 minus alpha divided by 2. And this symbol here corresponds to, well, what is this number that provides a certain area? So for example, so let's say this is my chi-squared distribution. Perhaps I have a 5 here for the actual number, and then this will be equivalent to chi-squared with some alpha divided by 2 here, a particular degrees of freedom, df for short, as well. And so the area here will be like alpha divided by 2. We'll look at examples as we go along. And so what one could do also is think of it from the other direction too. So we could have 1 minus alpha divided by 2 in the actual subscript there. That means the area to the right of this particular number underneath the curve here is 1 minus alpha divided by 2. The area to the left is alpha divided by 2. And the reason why we want to do this kind of stuff is because, as you might remember from our previous sets of notes, we're often always going to be looking at a situation like this where we have this random variable and we're looking at the probability that this random variable is between 2 different quantiles from that distribution, and we want that probability to be 1 minus alpha. More on that very shortly. So what I've done to help you understand this particular probability distribution is I've created this interactive Excel file for you. So let's say that degrees of freedom is 10. This is all drawn to scale. And I want this quantile for my chi-squared distribution such that the area to the right of it is 0.1. The area to the left is 0.9. Let me see if I can draw on this. And so if we look at the area underneath the curve, we would have 0.1 there. We have 0.9 there. Here's 15.9, about 0.99 if I round. And so that's what this little symbolic notation is actually meaning. We could look at other quantiles as well associated with 10 degrees of freedom. Take a look at, for example, now we're on the far extreme of the distribution. We're like right there. The area to the right of it is 0.001. The area to the left of it is 0.999. And that corresponding quantile is 29.58. Okay, let me do some erasing. As I said, that this is an interactive file, Excel file. So that means that if I want to, I could change my degrees of freedom, and let's get out of it, and I could see the plot update. So look what happens if I drop the degrees of freedom. Suppose it's 5. Now we can see the distributions moving to the left. In an intuitive standpoint, you should think about why this is occurring. Remember how the mean is equal to the degrees of freedom for a chi-square random variable? Well, if I go from a mean of 10 to a mean of 5, that means then, sorry to use the word means, that leads to us having the center of the distribution as essentially what the mean is representing, moving to the left as well. And we could even keep on going to 2, and we can see we really get a right skewed distribution. Even at 1, we get a very right skewed distribution as well. Now, as I'm making these changes in my plot, you can see then the corresponding quantiles are changing as well. Still, the area to the right of this first quantile is 0.1. Now, if I go back to 10, look what happens when I make it 20 or even 30. And eventually, you're going to go off what I've set the plot to show. And so this, this Excel file is, again, an introductory tool to get you comfortable with these chi-square quantiles. This probability distribution is very similar to what we've seen with the normal and the t-distribution in terms of like a notational setup here. A key difference between this probability distribution and the normal and the t is it is not symmetric about 0. All its values are always greater than 0 as well. The distribution is right skewed. Okay. Jump back over here to Word. Well, let's look at how we can use R now to find quantiles associated with this probability distribution, and probabilities too. So if I wanted to find the probability that a random variable x with a chi-square distribution with 1 degree of freedom is less than 3.84, what I could always do is go to calculus, where I solve the integral 0 to 3.84 of my chi-square distribution, where I've replaced nu with the value of 1. Instead, what we can do is use the p chi sq function. We've seen the p norm function, we've seen the t function. Now we have the p for probability chi sq function. And the way it works, we have again a q argument for the quantile, 3.84. We have an argument for the degrees of freedom, df, that is value equal to 1. And so we get about 0.95. Well, let's say I want to find the 1 minus alpha divided by 2 quantile from a chi-square distribution. In other words, what I want to find is this symbolic value with 1 degree of freedom. So what I could do is set up my equation. I have a probability of 1 minus alpha divided by 2. And I want to find that number, let's call it C, such that the probability that you're to the left of C is equal to 1 minus alpha divided by 2. And so I could do this integration, solve for C, and I get my answer. Instead, what we will actually do is use the q chi sq function, similar to what we've seen before for a q norm function, a qt function, and so on. So let's say alpha is 0.1 for our case. Then with q chi sq, I put in my probability of being to the left, 1 minus alpha divided by 2, and my degrees of freedom of 1, and I get 3.84. Lastly, if we wanted to actually do a plot to the chi-square distribution, so we would like to get this f of x value that we saw in the actual expression, well, you could actually program in the f of x value into R, or more simply, just use the d chi sq function. So to do a plot then of this particular probability distribution, I use my curve function as I've done before. My expression as a function of x for the x-axis is d chi sq. So it's going to be a function of x, degrees of freedom of 1. I want to plot it from 0 to 5 on the x-axis. It's going to be nicely represented by a red line. The line width is going to be 2 times the default. I put a nice little title in my plot with the main argument, y-axis label, x-axis label, and I'm going to evaluate this f of x value at 1,000 different values from 0 to 5 equally spaced. So I start at essentially a little bit greater than 0, then go to maybe, let's say, 0.1, 0.2, get f of x every single time. And then I can plot f of x. I'm going to draw a horizontal line at 0. And here's my plot. Similar to what we saw with the Excel file, the distribution is really, really right skewed here. And if we wanted to, we could do a chi-square distribution plot with degrees of freedom of 10 as well. Again, it's right skewed, but it's not so far up against the left-hand side limit. Now, most introductory statistics books will provide a probability table, like in the back of the book, where you can find probabilities associated with a chi-square distribution. There's no reason to use those tables anymore. We're just simply going to use R to find the probabilities or corresponding quantiles. Okay, so that's the introduction to the chi-square distribution. And the whole reason why we're talking about the chi-square distribution is because we want to make inferences about sigma squared, or population variance. And what ends up happening is that chi-square distribution plays a role as being part of the distribution for our corresponding statistic S squared. Okay, so hopefully you remember when we were doing inferences about the population mean. This is when we talked about, for example, the central limit theorem. We saw that y bar, our sample mean, has an approximate normal distribution to it. And eventually we got into talking about working with a t-distribution, and y bar played a role in that as well. Well, now we need a probability distribution for S squared, since we want to make inferences about sigma squared. And so to do this, we need to make an assumption, and we'll talk about the ramifications of this assumption later. We need to assume that y1, y2 down to yn, meaning these are random variables representing, we're taking sample size n from our population. We need to assume that these random variables come from a population characterized by a normal probability distribution, where each has the same mean mu, and each has the same variance as sigma squared. Now, this is what I actually want to make inferences about. Now, again, in a mathematical statistics course, one would actually prove mathematically that n minus 1 times S squared divided by sigma squared has a chi-square distribution with a degrees of freedom that's equal to your sample size minus 1. Again, don't worry about a proof like this. But this is kind of a nice result. And the reason why it's nice is it goes back to how we've approached similar problems in the past. So when we were working with the mean, the first thing that we did was something like this. Sorry, I'm kind of running out of space here. Where we took this quantity that was dependent upon y bar. We knew its corresponding distribution approximately, and because we knew that probability distribution, we could put one quantile from that distribution on the left, we could put one quantile from the distribution on the right, and we know what's the approximate probability that this quantity in the middle was between these two quantiles. We're going to do the same thing here. And if you remember, when we did work with this with respect to the population mean, this eventually led to a confidence interval. It led us to various inference procedures. Guess what? Same thing's going to happen here. So, since this quantity that's dependent upon S squared and sigma squared has a chi-square distribution, we can write this following probability statement. We get a quantile from our chi-square distribution. on the left, a quantile from the chi-square distribution on the right. Notice we don't, let's say, use the negative of this thing that's on the right, on the left side, because of the non-symmetricness, or it's, I shouldn't say non-symmetricness, I don't know if that's a word. The reason is because the probability distribution is not symmetric. Let me do some erasing. And so we know the probability corresponding to this random variable of this occurring is 1 minus alpha. So let's rearrange some terms. So what I'm going to do is divide both, or actually all three components of this inequality by n minus 1 times s squared. So you can see that division there as well. Then let's flip what's in the middle. So instead of 1 over sigma squared, now I want just sigma squared. Well, when I do that, I need to also flip then the corresponding quantities here. And based upon what you learned in algebra class, you're going to need to flip the inequality signs as well. Well, let's get this back in a place where I have the correct lower number and the correct upper number. So what I'm going to do is put this down here, put that up here. Now I can reverse my inequality signs, and I get this nice little statement. Based upon that, then, I can get a confidence interval for sigma squared. So I replace the random variable with its corresponding observed value. And so my 1 minus alpha times 100% confidence interval for sigma squared is what you see here. Of course, we could also get a confidence interval for sigma itself, the standard deviation, by just simply taking the square root of both the lower bound and the upper bound. Okay, so let's actually put this to an application. This deals with quality control and hand grenades. I think after you see this example, you'll see, yeah, I think it's very important to make inferences about a variance or standard deviation. So let's say that a particular kind of hand grenade has an average explosion time of 5 seconds after you pull the pin out. Of course, it's not necessarily going to be exactly equal to 5 seconds. There's going to be some variability. Maybe it might be 4.9 one time. Maybe it might be 5.1. Maybe it might be 4.8 seconds. Well, the manufacturer claims that the standard deviation between pulling the pin and explosion is 0.2 seconds. So let's test that claim. Take a random sample of 10 grenades. Each grenade's pin is pulled in a safe manner, and the number of seconds until an explosion occurs is recorded. So for the first grenade, it took 5.157 seconds. For the last grenade, it took 4.699 seconds. Okay. So let's actually take a look at some plots. Well, let me first show you how I actually got the data itself. So this isn't real data. I simulated it, meaning that based upon our corresponding probability distribution assumptions, normal probability distribution, I'm going to have R actually simulate 10 different values, like simulate the process of sampling 10 of these grenades. And the way I do that is to use R norm as my function that does that. R stands for random. R norm n equal 10, mean equal 5, standard deviation 0.2. So notice I'm actually simulating the data assuming that what the manufacturer says is true. I'm going to set a seed here so I can always reproduce my results no matter how I actually simulate, no matter when I simulate the data. We've seen setting a seed before with a sample function, if you remember that. If you're not for sure exactly what would happen if I don't set a seed, run this a few times without actually doing the set.seed part. I'm going to actually set my seed, and I get our corresponding observations. So from that, we can do box and dot plots, as we've done many times before. Oops, there we go. And here's my plot. And what we can see here is that actually The median, to remember by that thick line in the middle of the box, is actually less than 5 seconds. It's about 4.9 seconds. But we can see that sometimes we get a little bit more than 5. Sometimes we get a little bit less than 5 as well. Let's take a look at a histogram of the data. So I'm going to plot the stuff that's in Grenade, put a nice title on my plot, x-axis label on the plot, x-axis limits, I'm going to control those. And then I'm going to say freq equal false. What that tells R to do is to adjust my y-axis scale so it's not based upon frequencies as you would normally for a histogram, but rather it's rescaled so that I can actually plot a normal distribution or any kind of distribution upon it. So here's my actual histogram. Then I'm going to plot what would be, let's say, the best fitting or best estimate of a normal distribution to this data. So I'm going to take the curve functions we've done before. Expression equal, I want to plot the normal distribution as a function of x. I'm going to use the sample mean as the actual population mean, because that would be the best way to estimate that, and the sample standard deviation as the population standard deviation, color red, add it to the current plot. And this is what I get. Let me actually jump back over here to my Word document. So here's a plot of the data. What do you think about the normal probability distribution for the hand grenade explosion time? Do you think it follows a normal distribution? Well, these histogram bars are not following the same shape as what that curve is doing there. And one of the reasons why I purposely plotted this is because remember how I simulated the data. I did simulate the data corresponding to a normal distribution. And you might be thinking, okay, shouldn't the histogram kind of be mound-shaped or bell-shaped and symmetric around the mean of 5? Well, in our case, we only have a sample size of 10. And so because of that, sometimes it can be very difficult then to make a judgment. Did the data come from a normal distribution or not? So look, for example, what would happen if I actually simulated, let's say 1,000 values. So now I'm taking a larger sample of the actual from the population, and so this sample is going to be more or better representative of the population, and indeed, look at that, it sure does look that way. Let me set it back to the way it was. Okay, so let's find a 90% confidence interval for sigma squared itself. Now, the variance of all the grenade values is 0.03. So I plug that into my expression for my confidence interval. Sample size is 10, so I subtract off 1. Excuse me. Now I need to find the corresponding quantiles from a chi-square distribution. So this chi-square value right there, what that is representing, if I draw it out, is this particular value that goes way out here. The area underneath the curve is alpha divided by 2 there. 1 minus alpha divided by 2 to the left of it. I can now use my q chi sq function. I put in the 1 minus alpha divided by 2 because remember that represents the area to the left. Degrees of freedom of n minus 1, and I get 16.9. I do a similar thing for that left side quantile as well. Then we can find our interval. Take your sample size minus 1 times that variance, divide by the corresponding chi-square value, and do that both for the lower and upper bound. And here's the interval, 0.016 to 0.08 seconds squared. So in interpretation, I'm 90% confident that sigma squared is between these two numbers. Or alternatively, you could phrase your interpretation like this, that in 90% of similarly constructed confidence intervals, I would expect sigma squared to be within the corresponding lower bounds. Well, what about a confidence interval for sigma? All you do is you take the square root of the lower bound and the upper bound and you get the corresponding distribution, 0.1273 to 0.2871. Now remember what the manufacturer's claim was. Sigma was 0.2. Is there sufficient evidence to reject the company's claim that sigma is equal to 0.2? Well, sigma 0.2 is inside the interval. Sigma could be the 0.25. It could be 0.13. It could be anything between those two numbers. And so is there sufficient evidence to reject the company's claim? No, there isn't. Excuse me. Now, going back to earlier in the semester, we talked about this rule of thumb for the number of standard deviations. All data lies from its mean. Well, using what we've learned about this interval here, what we could do is come up with a range of time that we would expect then the corresponding grenades to explode. And so I want you to do that on your own. And think about what would be, let's say, the shortest time that it would take for a grenade to explode using this rule of thumb. If you have problems doing that, you need to ask a question. So here's something that's very important. Would you feel better about using a lower or higher level of confidence for this interval? Well, think of, let's say that you are, let's say, in the military and you're using these grenades. Which would you feel better about? A 90% interval, a 60% interval, or a 99% confidence interval? Oh, I would want that to be, that confidence level to be as high as possible. But what type of an effect would this have on the interval's length? You know, we've talked about that with respect to confidence intervals for the population mean. I want you to apply what you learned there to this new situation and answer this corresponding question. If you have problems with that, you need to ask during class. Okay, well, what about hypothesis testing? Well, we're essentially going to be playing the same game that we've done with other sets of parameters that we've found confidence intervals and then did hypothesis tests with. Now we just have a different statistic. Our critical values are going to be based upon a chi-square distribution, and we find p-values corresponding to that chi-square distribution as well. Okay, so here are some possible hypothesis tests to consider. I think all three of these particular sets of hypotheses could be of interest depending upon a particular problem. We're going to focus on this first one here. We're going to do a test of sigma squared is less than or equal to 0.04 versus sigma squared is 0.04. Now, why? Well, again, we often really focus on this HA here. Remember how we can control the probability of a type 1 error. And if one rejects HO, what that says is that there's a big problem with respect to when a grenade explodes. Excuse me. You know, you might not want to use this kind of grenade if you reject HO, because you know there's going to be a lot of variability in that explosion time, or more than what was actually advertised. So let's perform the test then. First of all, confidence interval method. We have a one-sided or right-sided test here, so that means we need a one-sided interval. And just like what we first saw for confidence intervals for one population mean, when we're finding an interval for this kind of situation, we need to find an interval such that you're dealing with a lower bound, and that upper bound is essentially, or upper limit is essentially unbounded. Now, you might be wondering, okay, why again do I calculate this number on the left side of the interval and I don't do it for the right? And it all comes down to the fact that if you reverse things, suppose you looked at it from the point of view of always calculating that right number, could you ever reject HO? And the answer is no. And the discussion of why goes back to what we learned earlier in the semester. Okay. So this is my confidence interval that I'm going to calculate. Now notice here, I only have alpha. I don't have alpha divided by 2. Again, we're doing a one-tailed test. we are working with just a one-sided confidence interval. So I'm only going to find one of these quantiles for my chi-square distribution. I only need to use alpha then, not alpha divided by 2. So I go through my calculation. I get 0.0187 for that lower bound. And so that's for when I'm working with the variance. If you take the square root of 0.0187, you get 0.1366. So then when we're dealing with sigma squared is 0.04. When we're dealing with sigma, we're dealing with 0.2. Notice that 0.2 is inside this confidence interval there. So because of that, there's not sufficient evidence to indicate a variance of more than what's stated, or a standard deviation more than what's stated. Now, you could also perform this hypothesis test using a test statistic and a p-value. And I'm going to say it once again, it all goes back to what we learned earlier in the semester with one population mean. The way that we approached that particular situation, we looked at a statement such as this, where we have some numerical value here that was a function of our statistic and our parameter of interest. We surround it by the two quantiles from the corresponding distribution so that we can say with a certain probability what's the probability that this middle value or middle random variable is between these two numbers. Then we take what's in the middle there and we say, let's now assume that HO is true. And what that means is now we substitute what the hypothesized value in the null hypothesis for sigma squared to be. We're going to call that sigma squared 0. And that becomes our test statistic. We will simply call our test statistic chi-squared, for the lack of a better name. So what are the critical values for a two-tailed test? Well, we see them right there. What are the critical values for a left tail or right tail test? It simply follows from this here. We will see shortly that being used in the example. What about a p-value now? Well, remember what a p-value is representing. It's a measure of how extreme the test statistic is relative to what you expect under the null hypothesis. In the past, what we've done is we've taken 2 times the probability, we'll put it in terms of the t distribution. A random variable t is greater than the absolute value of the observed test statistic. Now, we were able to do it like that because we had a symmetric distribution. Now we don't. So now we need to make some adjustments. But still, it's the same idea of measuring how extreme you are relative to the distribution itself. And so let's say that here is my chi-square distribution once again. And let's say my test statistic falls out here. Okay, we can see that it's closer, or it's more extreme relative to the right side than to the left side. So because of that, I could calculate this particular probability. It's going to be relatively small. The other probability I could calculate too, but I know that that's going to be large. It's going to be greater than 0.5 definitely. But again, as a measure of how extreme I am relative to this distribution, then what I'm looking for always is that smallest probability. In other words, the minimum of the 2 different probabilities that one could calculate. And then I'm going to take it times 2 because I have a two-tailed test. So that's how you would find the p-value. What's the p-value for a left tail or right tail test as well? It follows from the same idea. You know, if it's a right tail test, you're going to always find the area to the right. If it's a left tail test, find the area to the left. Okay, so let's take a look at then the hand grenades example again. My test statistic ends up being 6.85 when I go through the calculations. The critical value then, so one-tailed test. I'm sorry, it is a one-tailed test, but it's a right-tailed test. Notice how I have a greater than sign there. So that means then I have to go to the right side of my probability distribution to find that corresponding critical value. So for us, that would be the chi-squared value, where alpha is the area to the right of it, and I have 9 degrees of freedom. So I get 14.68. And here's a plot. So here is my chi-squared alpha, and then the corresponding degrees of freedom of 9. Here's where my test statistic falls. And I can see that that test statistic is not extreme relative to this probability distribution. And the area to the right here is 0.01. I'm sorry, 0.1. So do not reject HO because 6.85 is less than 14.68. There's not sufficient evidence to indicate a variance of more than 0.04. Okay. So again, what this is saying is that, to get the sample that we did is a reasonable thing to occur if the null hypothesis was true. That's the whole purpose of, or the whole, I guess, final result behind this, to explain what's going on. In terms of the p-value method, then again, I have a greater than there. So that means when I find my p-value, I need to find a greater. So suppose x is a random variable with a chi-squared distribution. I want to find the probability that x is greater than chi-squared. And in other words, if I go back to my drawing here, and do make sure you understand how I did the drawing, the corresponding code is in the corresponding program. Sometimes I say corresponding too much. So what I'm trying to do is find this particular area. I don't need to multiply it by 2 because it's just a one-tailed test. That area ends up being 0.6530. And how do I find that? I find that using the p chi-sq function. Alpha is 0.1, so do not reject HO because the p-value is greater than alpha. In the end, there's not sufficient evidence that can indicate a variance of more than 0.04. Okay. Now, I brought up earlier that this test statistic, and I guess the overall statistic itself that we were working with is n minus 1 times s squared divided by sigma squared. It relies, to get this chi-square distribution, it relies on the data essentially being characterized by a normal distribution. Unfortunately, in a number of real-life applications, that won't be true. And unlike what we have with doing a confidence interval for a population mean, where we also had that assumption when we were dealing with the t distribution, but I said that's okay if in most situations it's still going to work even if you don't have a normal distribution for your actual data itself. It's still going to work out well. Here, unfortunately, in this situation, the inference procedures that we just took a look at, it might not work out okay if your normal distribution assumption does not hold, which is too bad. And what's interesting is that in introductory stat books, most of them don't really talk about that aspect. They just show what I just have shown you here. But I do want to mention, well, what else could you do if the normal distribution does not work out? So I guess what I would begin with is that hopefully you have a large enough sample and you can make a judgment from a histogram of whether or not a normal distribution seems to be relatively satisfied for your data. But if it doesn't, then here are two options of how you could proceed. Now, for a large sample, the distribution of s squared can be approximated by a normal distribution with a mean parameter of sigma squared. So sigma squared is actually the variance of y1, y2, all the way to yn, and a variance of this quantity here. So what some people will do, they'll write it like this. S squared is approximately distributed as, so we've seen the tilde before to mean distributed as, the dot on top of it means approximately, and people will write it like this: a normal random variable with a mean of sigma squared where expected value of y sub I is equal to sigma squared. Oops. And a corresponding variance that you would put in there of this quantity here. This interval can work rather well if you have a large sample size. And the key is it doesn't matter what the actual distribution is of these y's that you have. A few years ago in one of my PhD level statistics courses that I teach to stat PhD students, we actually examine this in detail. And indeed, this interval can work very well if you have a large sample size. And to some respect, it might even be a better one to use all the time over the intervals that we just got done talking about. And I had thought about replacing this result with what we did. In the end, I decided to go with what we did because this is a standard way to approach the problem. But I do want you to have in your back of your mind, if you come across a situation like this, it may be worthwhile to explore using this kind of an interval, or explore using an interval based upon this result. Now, another approach that one could do is use a statistical procedure known as the bootstrap. Statistics doesn't have many things that have interesting names. This is one of the cases where we have this thing called the bootstrap. And what this is what's often referred to as a non-parametric statistical procedure, meaning it doesn't rely on any underlying distributional assumptions for your data itself, and it doesn't actually use let's say an actual distribution that you can write out for your statistic of interest. And the bootstrap can be used in a wide variety of situations, not just necessarily this one here. And one could use the bootstrap to find a confidence interval, to do a hypothesis test as well. And you don't have to worry about having any kind of normal distribution assumption. But based upon my investigations that my PhD students did in this particular class, what we have found is that it does take a large sample size too for this bootstrap to work well. And really, it wasn't necessarily working any better than this option number one that I gave you before. I will tell you that this bootstrap, what it does, it actually uses computing power to basically estimate a distribution for S squared, one could say, rather than, saying S squared has an approximate chi-square distribution if you do some stuff with it. Now, with the bootstrap, though, you got to be careful that there are a number of different ways to find confidence intervals with the bootstrap. Very often, most people use what's called a percentile interval method. That one actually often doesn't work very well. So it's unfortunate that people do that. Instead, what one should do is use what's called a BCA method, bias corrected accelerated method, or a studentized, or what's called a studentized confidence interval method. If you want to know more about that, I've actually taught a whole course on the bootstrap to PhD students. This was a different class than where my students did some investigations. And I do have a course website that's available that talks about the bootstrap for an entire semester. So for our course, generally speaking, you can use the methods that we had spent most of our time talking about. We may explore a little bit further, like number one or number two here, depending upon if we have time. So that's the end of this particular section.